Welcome to Monterrey, Mexico, a city widely recognized for its industry, commerce, and job opportunities in recent years, where every day the millions of inhabitants of the city of Monterrey embark on their daily activities, such as shopping, going out with friends, working, going to the mall, exercising, buying clothes for the regular routine, barbecuing, and shopping. However, not everything can be good news, since in recent years the city of Monterrey has been involved in various environmental controversies that put at risk the quality of life of its inhabitants. Situations such as water pollution, air pollution, drought that has been affected in recent years, to name a few. It is important to note that some of these situations, at first glance, may be silent and unnoticed, but have massive consequences on the general population.
This is why, this year, we decided to look at fast fashion, which promotes the practice of mass production of clothing and textile products, with the characteristic that the clothes are of poor quality, so that the general public has the perception or feeling of acquiring new clothes quite often, and generate an endless cycle of purchase and discard. At first glance, this might seem innocent in terms of impact, but this situation increases when you learn that most of the synthetic fibers used in clothing, generated from fast fashion, use chemicals that are very difficult to degrade, taking hundreds and hundreds of years to reach their total degradation. And when these garments reach the landfill is when a real problem occurs, as the molecules of nylon and polyester can infiltrate into the soil and water bodies, contaminating vegetation, soil, water, and more, causing a risk for the populations that might be near these areas, and compromising the quality of water that is for our consumption. In general, fast fashion represents an environmental problem from the point of view of industrial production and consumption. Since we did a study that indicated that more than 60% of young adults in Monterrey came to buy more than 30 outfits per year, and only discarded them when the clothes were completely unusable. It should be noted that to produce a single pair of pants, hundreds of liters of water are used and polluted for its production.
The most obvious and logical course of action to solve this problem is to stop production. But taking into account that this industry takes more than 30% of the economy of the state of Nuevo León, in addition to representing 80% of the source from which the population obtains its clothing, it is not seen as a possibility. This is where the question arises: is there anything that can be done about it?
Good news! There is! Here at IGEM FCB-UANL, we have looked deep into the problem that fast fashion represents, as well as the social implications it bears. In our community, we discovered that 55% of young adults lack awareness about the fate of the clothing once it becomes unused, as well as the environmental impact of the materials used in mass-produced garments. Motivated by this insight, we embarked on a mission to develop a biological system with the ability to break down textile pollutants. We called this Fiber Eater. Our first task was to determine which specific molecules held the utmost significance for degradation.
It is well known that most synthetic fibers include various microplastics in the form of polyesters. However, there are far too many variations to work with. For this reason, we contacted PhD Gabriela Vázquez, an expert in microfibers, and alongside her and her feedback, we decided to focus in three main components: PET, PTT, and nylon. This molecule uses terephthalic acid, petroleum, ethylene glycol, and other compounds to be produced, which are the ones that cause the most damage to the environment. In fact, it has been reported that these polyester products take up to 60% of all clothing production, which, in terms of fast fashion, it's quite a lot.
These components are often mixed with cotton to prevent hail damage. but they can't prevent environmental consequences. However, we identified which pollutants were the most important. We needed to build our system capable of degrading these compounds into something more useful and less contaminant. Even something like ethyl biofuels, but for now, we need to be sure that we can degrade them. To develop our system, the initial step was to pinpoint the enzymes essential for achieving our objectives. To accomplish this, we extensively utilized various databases and employed a range of parameters in the process. 1. We needed proof polyester and nylon degradation reports. 2. We needed to make sure that all our enzymes could be expressed with E. coli. 3. We needed all enzymes to work within a similar range of temperatures and pH to enhance system productivity. And 4. We needed to have access to 3D structures of the proteins so that we can predict their catalytic activity within our system.
And after weeks of hard work, we stepped upon these 4 enzymes: PETase and METase from Ideonella sacchayensis, which chemically break down PET in order to obtain nutrients for cell growth. METase specifically breaks down ester bonds. Cutinase from Thermobifida fusca, which chemically bonds and hydrolyzes PTT, liberating terephthalic acid. And nylon 6 hydrolase from Flavobacterium species, which hydrolyzes nylon 6 to produce caprolactam, a compound that can be reprocessed in non-harming industrial processes. Among all the members of the team, we decided to use 4 important enzymes: PETase and METase to degrade PET, acutinase for PTT, and nylon 6 hydrolase for nylon 6. We plan to express all of these enzymes on Escherichia coli using 3 PSB3K3 plasmids that looks like this.
Here we can see that the first plasmid uses both metase and petase, using an inducible promoter P-VAN-CC, which will enable enzyme production when there is vanillic acid on the medium. With the help and feedback of PhD Ever Torres, we added a third protein, hydrophobin, which allows metase and petase to work together synergistically. For this circuit to work, we can notice these 2 sections, R2D and R1AD, which are peptides that enhance hydrophobin stability and enzymatic activity. At the end, we can see our RRBNT1 terminator. Using the same promoter and terminator, we have plasmids 2 and 3, which allow the expression and catalytic activity of cutinase and nylon hydrolase respectively.
Now, as we completed our system, we needed a way to test it. For this reason, we designed a mathematical model where we performed 2 main tasks: to determine the behavior of the system proposed and to determine the interaction of each of the enzymes used with their respective polyester to be degraded. For the first point, we decided to make a programming code in Python language that will help us to solve ordinary differential equations that are relevant to the satisfaction of 3 points. How will the input of the proposed inducer behave? How much transcript will be produced for the concentration of the inducer? And how much enzyme will be produced according to the transcripts produced. Once we had established the equations we would use, we now needed to solve 3 other important points: the automatic solution of the equations, the handling of relatively long times in solving the equations, and the graphing of the results. So we use SciPy, NumPy, and Matplotlib packages respectively for each of the points. We obtained the following results.
The optimal concentration of inducer to be used in the system is 1 molar, which shows a parity in the internal concentration with respect to the external concentration. That is, if the inducer outside the cell is 1 molar, the concentration of inducer inside the cell will eventually be 1 molar. Transcripts are generated in the hundreds. At first glance, one can infer a low production, which will have an impact on the enzyme levels that will be generated from these transcripts. but we wanted to test the efficiency that the production of this amount of transcripts would have. Finally, enzymes are produced in quantities of millions of amino acids. This does not mean that millions of enzymes are produced, but rather that millions of amino acids are produced from each enzyme, which are translated and form the amino acid chain that becomes the enzyme.
Having this information at hand, we conducted an assessment to ensure that the enzyme concentration in the bacteria remained below the metabolic load threshold for E. coli. Our investigation, supported by relevant literature, yielded positive results. To conclude the gene expression analysis, we extrapolated the data to determine enzymatic activity. Notably, we observed a higher enzymatic activity in the case of the cutinase, while metase exhibited a comparatively lower activity level. This outcome indicates potential areas for improvement in our future endeavors. To address our second objective, we conducted a molecular docking procedure using two programs, Avogadro and Chimera. Initially, we searched for the PDB files of the enzymes along with their respective ligands to examine the specific interactions between the enzymes and their corresponding polyesters. This process generated molecular docking results. Regarding the enzymes responsible for PET degradation, betase and metase were observed to bind to polyester, subsequently breaking the ester and the carboxylic bonds. This interaction results in the breakdown of PET into its fundamental components, primarily terephthalate and ethylene glycol. Conversely, cutinase binds to the ester bonds of PTT, leading to its hydrolysis and the subsequent separation of the polyester into three compounds: terephthalic acid, BHBT, and MHBT. Finally, nylon 6 hydrolase targets the amide bonds in nylon 6, initiating the hydrolysis process that leads to the degradation of polyester. The end product of this process consists of caprolactam monomers, which can be repurposed for various applications.
But like any project, this one has its risks. So we took care of the systematic risk assessment of all the project components with the help of spreadsheets to verify that all components were safe, including the possible misuse of our technologies through a DURC analysis. In a more complete way, a toxicological analysis and the application of containment and reuse measures to avoid the generation of toxic compounds was also performed, together with an analysis of the laws that are applicable to the project in order to comply with the law and perform it correctly. In addition, we solicited stakeholder input, which helped us steer the project on a safer path, and we train our team members to effectively mitigate all potential project risk and provide adequate training. Finally, as a biocontainment measure, the creation of a kill switch was established, which has a toxin system. The kill switch will only be activated in the presence of valine, which is the inductor of the system. And in the presence of light, these conditions promote the production of a toxin that causes the death of the bacteria present in the system. This is done in order to control the system in a safe way, avoiding a malfunction, incorrect use, or the release of GMOs into the environment, which is the purpose of biosafety. Our activities didn't stop there. As a team and as scientists, we recognize that science at this level can be quite hard to understand for people outside the area. And given that we live in a world where science and technology play a crucial role in addressing global issues, it is essential to inspire the next generation to explore science. For this, we have designed theoretical practical workshops to awaken the interest of students, especially high school students. These workshops included introductory presentations and live demonstrations of laboratory techniques, such as agarose gel electrophoresis, where students themselves created gels and used micropipettes. These workshops did not remain in theory. They also gave students the opportunity to perform laboratory work, where they learned to use common lab equipment and performed hands-on experiments such as DNA extraction. We believe this hands-on experience is essential for students to understand
how science works in real life and to stimulate their interest in scientific careers. We held these workshops at 2 local high schools, where our target audience was teenagers between the ages of 15 and 17. As part of our commitment to evaluating the impact of our workshops, we conducted surveys after each workshop. The results show that the students liked the practical part and that their level of knowledge increased.
In addition to the workshops, we also implemented an apprenticeship program, where more experienced members of our team helped new members gain hands-on experience in the lab. This included plasmid DNA extraction protocols and other advanced techniques in synthetic biology. Additionally, we implemented a synthetic biology tunnel at different schools aimed towards college students and high school students. Our goal is to educate the public and demystify synthetic biology. The tunnel consists of 10 modules that address various topics from molecular biology basics to genetics to ethics within the synthetic biology field. We also developed an environmental education manual for teenagers where we discuss topics such as responsible consumption and sustainable fashion. We want to raise awareness in the community about the importance of caring for the environment and how small actions can have a big impact. Fiber Eater, as a biological system, aims to solve fast fashion's consequences. But as a team, it aims to be an impactful and meaningful movement towards responsible consumption, sustainable cities, scientific awareness, and overall a better environmental quality for everyone. We would like to thank everyone that helped support the project and the team throughout the season. Stick around to see what the team accomplishes in the future.